Final example with logistical differential equations, and again, this one's a little more complicated, but it's a great example, it's great use. Again, they're looking for us to try and come up with the Diff EQ that represents the data which is given. All right, we're talking about the population of people on a beach. All right, and so we're given, we know what the model overall happens to be. We're told that the maximum carrying capacity of the beach is 1,200 people, and then we're given a little bit more data. We're given the fact that there are 200 people on the beach at 10 a.m. and that at that same time the rate is increasing at 400 people per minute. And so the question now becomes, which one of those 5 options that you see on your paper happens to be the Diff EQ, which represents the model of how the growth is occurring? So we have to use this data, we have to use this model to try and come up with an answer. Right? Now, we're given M. All right. We're also given a population, right, at 10 a.m. So at 10 a.m. we can plug in, we don't actually have anything for time right here, so we have to plug in the 10. But we can plug in the 200 for the P. All right. And then we also have this 400 people per hour. All right. Well, that's a rate, the rate that the population is changing over time. Which variable does that happen to be? Right? Our units tell us, all right, people, which is population, over time. So this is people over time, or dp dt, because it's a rate. So we're given dp dt, we're given p, we're given m. What we're not given is k, but we can find that because we can plug everything else in. So let's go ahead and do that. All right, so we know that the rate of the change is 400, and that's equal to some value k, which we don't know yet, times the population, which is 200, oops, yep, there we go, times the difference between the maximum population, which is 1,200, and the current population, which again is 200. All right, so let's calculate this, figure out what k is, and then we're going to have our answer. So we have this is going to be 1,000 right here, and we're going to multiply that by 200, k, and that's equal to 400. All right, so 200 times 1,000, so let's see, we got k, and then we got 2, and then 1, 2, 3, 4, 5 zeros after that. Okay, and that's still equal to 400. And so now we can divide by that 200,000 in order to come up with the value of k. All right, so k is equal to, we're going to eliminate a couple of zeros there, so we have 4 going into 2,000. 4 goes into 2,500 times, k is equal to 1 over 500. So now that 1 over 500 is going to go back in there. Our maximum population is going to go right in for there. And then this model will work for any population whatsoever. So we're looking for what seems to be answer C.